Yeah, thanks for giving the opportunity. My name is Patrick Diehl, and I will talk the first 50% of our talk. And then Gregor Daiss takes over because he did all the implementation stuff and was implementing our compute kernels and cockers. And he will tell about more of his struggles he had with vectorization there. Okay, the motivation here. Here you see an image, and this is the peak brightness of the rare 2002 red nova V838. And this, what was happening later is people could observe the red light curve emission there. And so you have the observations. And now many teams over the world use different code to simulate this event, to reproduce this light curve. And we want to simulate the merger and obtain the light curve, not in a post-processing step, as most people did in the available literature. We wanted to include radiation in our code and get it directly in the simulation without a post-processing step. And if you want to learn more about these observations here, we put the paper here, but it's not really the main topic of our talk. It's more like the main thing we want to do. And therefore we did a lot of compute nodes. And yeah, this is our motivation. And the overview is, I will briefly introduce the software framework, OctoTiger, the astrophysics application, HBX, an asynchronous many-task runtime system we ported to this new architecture. And also we're using cockers within HBX to schedule our tasks and also do all the compute kernels. And then the second part and the conclusion and outlook will be done by Gregor, and he will talk about the scaling results and some of these things he did on Ookami to port our code and what we learned and what was going well and where we have experienced some challenges. So for the software framework here, we have OctoTiger. It's an open source program and it's simulating the evolution of stars systems based on the fast multipole method and adaptive octrees. OctoTiger has 3 modules. We have a hydro module, we have a gravity module, and we're working on the benchmark of radiation. And once we have this benchmark, we have all the 3 modules we need to simulate the light curve. And for communication, we can use MPI libfabric, and we have backends for CUDA. We have a HIP backend for AMD GPUs, and we recently added cockers, so we are more hardware independent with our kernels. And in this talk, we will focus on how we were using cockers to get our code run on Ookami. And here you see the reference, the benchmark and introduction of the paper, and OctoTiger's logo. And here's an example of the merger simulation. You can see the blue star, you can see the larger star, and you can see that we have adaptive mesh refinement. And here in these lines, you can see we have a finer mesh at the smaller object, we have a coarser mesh, and then over time here, after 2.6 orbits, you see that the mesh is refining in the center, where the stream started to go to the second star. Yeah, and so this means if you have more and more exchange here, we have much finer meshes, and we have a really heavy load imbalance on our system. And this is a time what we're struggling with, and we have to do a lot of things to do work stealing and get these things efficiently simulated, because over time, more nodes have more work, some has less work, and we have to do a lot of things with work stealing to get efficient simulations there. And here is a reference where we were running on NERSC, and we were doing a run with billions of tasks with a really large scale simulation, and the images are took from this publication. And here you see a more global picture. It's a fully 3D simulation, and after 3.4 orbits, you can see that the stream initiated and the 2 stars started to merge, and it's from the same application. And HBX is also an open source C++ standard library for concurrency and parallelism. And HBX exposes a uniform standard-oriented API for ease of programming parallel and distributed application. And HBX provides unified syntax and semantics for local and remote operations. So this means we hide all communication and all these calls from our user using an abstraction level. And from the user, you do not see if you do something for a local implementation or for a distributed one, because all this communication is hidden. And it also exposes a uniform, flexible, and extendable performance counter framework, so we can measure memory bandwidth and everything directly in HBX using this framework. So it's quite easy for us to do a lot of measurements while we run the simulation. And the last thing is, so recently HBX was added as a backend for Cockos. And so we have this concept of futurization, which was introduced in the C++11 standard. And so what now is possible is that we can use Cockos, and then we can launch a kernel code on a GPU or on a CPU. We get this future back, and then we can concatenate these futures to describe the data flow. But Gregor will tell you a lot more about this Cockos integration. So this is just the global picture. Yeah, and HBX combines tasks via futures in different ways. And OctoTiger uses Cockos for compute-intensive kernels, so we can run on the CPU and GPU. So we can fire one kernel on a CPU, one on a GPU. We get these futures back, and then we can say, only do this kernel when this kernel is finished on the GPU, then execute this one on the GPU, or vice versa. And OctoTiger's Cockos kernel use Cockos SIMID types for explicit vectoration. And this is the part now Gregor takes over this talk and will tell you a little bit how we struggled and what we had to do to get OctoTiger running on Ookami.
Thank you very much. So let's jump into the scaling results. Could you go to the next slide, please? Right, so basically, first, OctoTiger, as you have seen, is a bit of an oddball given our dependencies of other frameworks. So we have to check that everything with HBX is working on the machine, everything with Cockos is working on the machine. And so the purpose of our first test is basically check how the node level scaling and distributed scaling for basic test is working with OctoTiger and HBX, and test if our SIMD speedup is working. So for the SIMD speedup, we immediately ran into the problem that we could use the neon SIMD types within the Cockos SIMD library. But for SVE, they are recommending to use basically a generic SIMD type of a given length, and then use auto-vectorization, and naturally that didn't work. So that's why in the following slides, we will now just look at the neon types for now. So we have 128 bits. Best speedup we can get with that one, given that we are doing everything with double, is 2. So the setup for our test is, well, we want a scenario that runs on one core, but is at least large enough to get distributed to some nodes as well. So we run a gravity-only scenario using the fast multiple method. Since this is the method in OctoTiger that usually scales worst, it's also basically a good test for that. It scales worst because we have the tree traversals, one bottom-up tree traversals and one top-down tree traversal. So that usually limits scalability. So we are just using 7,000 subgrids for this test. So it's a rather small scenario, but it will do for this. And we will see the results on the next slide now. So as you can see here on the x-axis, we have the different core counts. So we start at one core, scale up to the entire 48 of a node. On the left side, we see the runtime. And on the right side, I also plotted the parallel efficiency for the solid lines. So just to give you an overview of how we are doing. So overall, we have 2 scenarios, basically. As always the same physics scenario, but one time we use the neon SMD types, and the other time we use basically no SMD types at all and run everything with normal double. So as we can see, there is a bit of a speed up with using the neon types, specifically a speed up of 1.4. We don't reach the full speed up of 2 simply because not everything in the tree traversal is entirely vectorized. So for example, with AVX2, we usually get a speed up of 2.5 here instead of 4. But overall, at least our SIMD implementation is working on the machine. It's now more a matter of getting it to work with the SVE types as well. So instead of being limited to the neon instruction, that we can also use the full vector width of the platform. So this is basically how we are currently doing on a node level. So basically vectorization sort of works, and parallel efficiency is usually between 80 and 90%. So it's doing all right for that, given that we have not yet optimized it at all for the platform. Then on the next slide, we will also take a look at scaling the same scenario up to a couple more nodes. So now we are going from 1 node to up to 8 nodes. So basically almost 400 CPU cores. As we can see here, the runtime is now dropping below 1 second for the when we are using the maximum core count. So we are basically running in 0.75 seconds. So at this point, our scalability sort of goes under simply because our scenario is getting a bit small. But overall, the distributed version also works. So basically, next up on our agenda is also like running more tests with larger scenarios and adding the hydro part. The hydro part works, but we haven't yet haven't done any scaling tests with it just yet. So this actually already brings me to our conclusions. So our conclusions, basically, if you go one slide further. So we got OctoTiger and the entire toolchain, so HBX, Cockos, and all other dependencies working on Ookami. So we are quite glad that that is out of the way. The node level scaling sort of looks like what we would expect. And the distributed scaling gets more interesting once we run larger scenarios. So that's basically up next. And other than that, the Cockos SIMD implementation that we use, it's working quite fine for neon types, but of course we don't really want to do neon SIMD on Ookami. So basically the next step would be figuring out why the SVE types are actually not working. Because currently I'm not entirely clear on that, since basically it should work, but it doesn't. It's always like this. But basically those are our next steps. And other than that, we are trying to get basically better scaling numbers now with our new Cockos HBX implementation. Of course, we want to port it, as I just said, to SVE and vectorize some more methods to get to the full SMD speed up. And other than that, on the physics side of things, we are currently trying to implement radiation. And since we use Cockos anyway, we also want to run it on AMD GPUs and are currently optimizing for that. So there's quite a lot of different projects going on with OctoTiger. And basically, I think we are already over the 10 minutes. So let's put a pin in it. And thank you for your attention. Do you have any questions?
Let me jump in with a quick question. I'm really excited to see Cockos on here. And if I understood correctly, you said that Cockos, in principle, does support SVE, but just for some reason, it's not generating the SVE code right now.
So usually the Cockos MD types are basically, you use the types and it translates to the correct intrinsics, like it does that within the code. For SVE, they didn't do that. So they basically just do the correct loop and put a compiler pragma before that for it to vectorize. And basically that didn't really happen for us, or at least didn't give us any speed up. Oddly enough, I didn't get any warnings about the loop not being vectorized. So it's quite an experimental thing yet, their SVE support. I think the pull request within the Cockos GitHub repository was accepted like mid of last year, but I don't know how many people are actually using it right now. So I actually had to patch it a bit to even compile with our kernels. So we are at this stage. So there were some like conversions in there that got instanced for our kernels and they didn't work. So I had to patch that. So it could be a whole number of things that could have gone wrong here.
Yeah, fascinating. And my bet is the GNU compiler might have the best chance of vectorizing this. Oddly enough, for C++, it seems to do a great job. Again, modulo not having any vectorized math.
We'll try that probably next. Like for this entire thing, we use the ArmClang compiler.